Trust in agentic AI isn't an intrinsic property of the model. You can deploy a state-of-the-art foundation model and have it behave dangerously in real-world deployment. Or you can run a modestly accurate model safely if the architecture is engineered correctly. As agentic systems move into operationally critical domains, clinical decision support, industrial multi-domain operations, judicial assistance, energy infrastructure, this stops being a philosophical debate and becomes an engineering imperative. We need an architecture where trust is a measurable property of the system, not just a declaration. Today, we're breaking down Trace, a metrologically grounded engineering framework for trustworthy agentic AI. Trace combines a four-layer reference architecture with an explicit split between classical machine learning and LLM validators, a stateful orchestration policy, bounded human supervision, and a new metric for model parsimony called CPR. Let's start with the landscape. The current literature addresses trustworthy AI through disconnected streams. You have clinical frameworks like Future AI that establish principles but lack metrological grounding. You have hierarchical oversight systems like tiered agentic oversight, or TAO, which demonstrate error reduction but are limited to clinical domains, rely too heavily on LLMs for routing, and conflate model selection with orchestration policy. You have metrology papers that transfer VIM and GUM apparatus to ML classification, but they don't address agentic architectures. And you have arguments for model parsimony, but no formal metric. Trace closes this gap. It unifies a multi-layer trust architecture, cross-domain instantiation, a metrologically grounded metric suite, and a quantified parsimony principle into a single engineering blueprint. Trace rests on 6 design principles, but the core engineering value lies in the 4-layer reference architecture. Layer 1 is the deterministic or physics-based core. This is non-generative, interpretable, and stable logic. We're talking rule systems, control theory, enumerated protocols, physical models, and compliance scaffolding. This layer serves as the primary trust anchor of the system. A key architectural distinction here is that unlike TAO, which implements routing and rules through an LLM orchestrator, Trace separates Layer 1 as an independent, non-learned, formally verifiable layer. Layer 2 is the learned component inventory. This is where we introduce the L2A versus L2B split, driven by the model parsimony principle. Layer 2 defines what the system can do, while the invocation policy is handled by Layer 3. Each invocation is stateless and accountable to its calling policy. L2A is specialized, or classical machine learning. This includes gradient boosting models like XGBoost and CatBoost, random forests, isolation forests, SVMs, and classical neural architectures like CNNs, LSTMs, or transformer encoders for sensor fusion. You deploy L2A where inputs are structured, latency is critical, reproducibility is required, and probability calibration is formally verifiable. Think of the calibration work by Gu et al., or the efficiency arguments for small models in agentic subtasks. L2B is the generative or LLM validator. LLMs and generative models are used as contextual validators, semantic reviewers, and inconsistency detectors for free-form data. Crucially, L2B is invoked only where the task genuinely requires linguistic understanding. The L2A-L2B boundary makes the use of large language models a deliberate design decision based on fitness for purpose, rather than an architectural default. Layer 3 is the orchestration and escalation policy. This is an architecturally separate stateful policy layer operating on task state, including passage history, accumulated confidence, risk context, and cost and latency budgets. The policy specifies which L2 components are invoked, and in what order. It handles reinvocation with adjusted context, and manages cost, accounting via a tier cost coefficient. The escalation trigger to Layer 4 is specific. It's not based on low confidence. It's triggered by a joint condition of high risk and high confidence. A confident error in a high-risk context is more dangerous than acknowledged uncertainty. Escalation also triggers if Layer 3 detects inconsistency between L2 components, or if the reinvocation budget is exhausted. This decouples model class selection from invocation policy, removing the safety parsimony trade-off found in systems that conflate these concerns. Layer 4 is bounded human supervision. This provides final accountability, veto rights, and calibration of AI authority bounds. Human oversight is treated as an architectural layer with measurable workload, not a cosmetic safety net. Entry to Layer 4 is determined by Layer 3 policy, not by direct requests from learned components. Now, how do we measure trust? Trace specifies a trust metric suite mapped to metrological standards like GUM, VIM, and ISO 17025. This extends the metrological apparatus from ML classification to the full agentic lifecycle: ingestion, inference, escalation, and human adjudication. The suite includes layer-wise metrics. Layer 1 tracks rule coverage rate, rule consistency index, and update traceability coefficient. Layer 2 monitors context relevance precision, context freshness index, and input perturbation stability rate. Layer 3 evaluates escalation precision, tier cost coefficient, and false positive attenuation. Layer 4 measures review burden index, override rate, and signal-to-noise ratio. Cross-cutting metrics include evidence trail completeness and calibration error. But the framework introduces a first-class design principle for parsimony, the computational parsimony ratio, or CPR. CPR is the ratio of the resource cost of the most economical model that adequately solves the subtask to the resource cost of the deployed model. A CPR of 1 indicates an optimal model choice. Value substantially below 1 signal architectural overhead. Resource cost encompasses latency, compute, training, and operational expenditure. To the best of our knowledge, CPR is the first formalization of complexity performance ratio as a quantifiable metric in trustworthy AI. It surfaces when you deploy an LLM where a gradient-boosted classifier satisfies the required calibration and accuracy, and it provides an auditable artifact for certification bodies. The universality of trace is demonstrated through 3 instantiations across operationally critical domains. First, clinical decision support. In this foundational instance, Layer 1 handles rule-based clinical logic compatible with traceability principles. L2A uses classical ML for structured prediction, risk scores, vital sign time series classification, and laboratory data modeling. L2B serves as an LLM validator for freeform clinical notes, performing contextual consistency checking. The Layer 3 escalation policy handles routine cases via L2A risk scores with calibrated probabilities. When boundary confidence is reached or complex context requires verification, L2B is invoked. Mandatory clinician handoff triggers on joint high-risk and high-confidence conditions, or L3 detected inconsistencies. Second, an industrial multi-domain platform for upstream oil and gas operations. This system spans technology, operations, and administrative subdomains. Here, the subdomain-to-layer matrix shows how model parsimony applies adaptively to evidence types. In technology and operations, L2A dominates. Sensor signals, time series data, and equipment telemetry benefit from classical ML's low latency and formally verifiable calibration. In the administrative subdomain, the dominant pair is Layer 1 and L2B. Regulatory and contractual rules are formally specified in Layer 1, while semantic review of freeform contract text and unstructured documents is the natural target for L2B LLM validators. A master orchestrator coordinates cross-subdomain pipelines, demonstrating that the architecture transfers across principally different data types within a single platform. Third, a judicial AI assistant, partially implemented within the EU Provo Justice Project. Layer 1 encodes procedural and substantive legal norms. L2A handles classical classification for document categorization, precedent relevance ranking, and named entity recognition. L2B performs case material analysis, precedent semantic correlation, and hallucination verification. Given that commercial legal RAG systems can exhibit hallucination rates around 17%, this multi-layer oversight is critical. The escalation policy requires juridical review before execution when claim stakes are high, and the recommendation is confident. Let's revisit the relationship to existing work. Tau supplies empirical facts that trace preserves. Tiered oversight reduces individual agent errors, and confident errors in high-risk contexts are dangerous. Trace reinterprets these within a layered architecture. Tau's finding that descending capability is safer is valid within a single model class, but Trace decouples model selection from policy, making this a calibration anchor rather than an architectural norm. IWA addresses a complementary problem. IWA provides a protocol-level solution for heterogeneous foundation model collaboration via the Tsahilu interface. Trace and IWA are not competing. IWA's Tsahilu protocol is a viable implementation of the Trace L28 L2B boundary. Conversely, Trace supplies the Layer 1 deterministic anchor, the Layer 3 stateful policy, the Layer 4 supervision layer, and the metrological metric suite that IWA does not address. Trace operationalizes trust and model parsimony as engineering outcomes. It shifts the design question from how intelligent is this model to what is this system permitted to do, on what grounds, under what supervision, with what measurable uncertainty, and is the right type of model being used for each subtask. By combining a 4-layer reference architecture, a strict L2A L2B split, and the computational parsimony ratio, Trace provides a reusable engineering blueprint for building agentic AI systems that are provably trustworthy in the domains where failure is not an option.